In this video, I'm going to be talking about displacement reactions. That's displacement reactions. Now, in the previous video, I talked about the reactivity of the different halogens. And in this video, what I'm going to be talking about is how this reactivity links to the ability of the halogens to basically steal electrons from each other. So in the previous video, I talked about the whole idea that the general equation when they react, particularly when they're being reduced, is X gains 1 electron, and that forms the halide ions, which is so X minus. And since it's gaining an electron, this is being reduced. And because it's being reduced, this must have got an electron from somewhere. And it probably got that electron from oxidizing another substance. And so because of this, we often refer to halogens as being a type of oxidizing agent. We can say that they're oxidizing agents. And this is simply because they're able to cause other elements or other substances to be oxidized. And since the tendency to be reduced decreases as you go down a period, the ability of the different elements to cause another substance to be oxidized in terms of the halogens also decreases as you go down the period. And we're going to see how this trend can now affect the ability of these halogens to displace to basically steal electrons from each other, and how we can actually observe that. So what I've got here is a table, and it's basically a table which has the halogens here, and this section basically is asking is a displacement reaction gonna occur between if this halogen is mixed with this halide ion, or inside the aqueous under aqueous conditions. And so I'm going to put like yes or no inside of these sections. And this part is just for the ionic equation of whatever reaction would happen here if it happens. So before I go into the ionic equation part, and after I go into this part, what I'm going to do is explain how you can basically derive an ionic equation. But before I do that, let me just go into whether or not these reactions will occur. And if you want, you can actually maybe try and answer these questions, fill in these boxes here on a paper or something. Okay, so let me fill this in. So first of all, we've got chlorine and chloride ions. Is chlorine gonna displace the chloride ions? Is it gonna steal its electrons? Now, if it had a greater oxidizing ability, it would steal its electrons, but it doesn't have a greater oxidizing ability, so it's not going to steal its electrons. So the answer would be no. There's not going to be a displacement. I actually draw that in red. There's not going to be a displacement reaction here. Is bromine going to displace chloride ions? No, bromine is has a less of an oxidizing ability. It's it's a less strong oxidizing agent than the chlorine. So no. Is iodine gonna displace it? No, for the same reason as bromine. Is chlorine gonna displace bromide ions? Now, chlorine has a greater oxidizing ability, so the answer is gonna be yes. It is gonna displace bromide ions. Is bromine gonna displace itself? For the same reason why chlorine doesn't displace chlorine, because it's equal oxidizing ability, the answer is gonna be no. Let me draw no in red. No. Is iodine going to displace bromide? No, iodine has a less of an oxidizing ability than bromine, so no, it's not going to displace it. Okay, so on to the next column. Is chlorine going to displace iodide ions? Well, chlorine has a greater oxidizing ability than iodine, so the answer is going to be yes. Is bromine going to displace iodide ions? It has a greater oxidizing ability, so the answer is going to be yes. Now, is iodide going to basically displace its own ions? Well, they've got equal oxidizing ability, so no, it's not going to displace iodide ions. So these now I filled out this table. And before I, as I said, before I go into going on to filling out this table, which is where I'm gonna write out the different ionic equations for the displacement reactions that do happen. I'm gonna explain how you can derive an ionic equation. So, but first of all, let's look at this. These boxes here correspond to these boxes, so no reaction happens in these three columns. So NR, no reaction, no reaction, no reaction, no reaction, no reaction, and no reaction. So anyway, let's go on to deriving an ionic equation for the displacement reaction that happens. So let's take an example. So imagine chlorine finds its way into a solution of potassium bromide. So that's KBr. And it's going to displace it because we have chlorine. Is it going to displace bromide ions? And the answer is yes. So let's draw out an equation for the reaction that happens. Yeah, this is the molecule of hexane. I'll get onto that later on. Let me find some space. Let's scroll down. Okay, so chlorine is going to be aqueous and it's going to be CO2. And it's going to react with the KBr. So KBr. And that's going to produce KCl and Br2. Now, I need to balance this equation, so let me go about balancing it. I'm going to use a green pen to do that. Chlorine, we've got 2 atoms of chlorine here and only 1 here, so we need to put 2 there. Potassium, well, now we've got 2 potassiums on this side, so we need 2 potassiums here, so I need to put 2 here, and we've got 2 bromines here and 2 bromines here, so it's now balanced. And let me just add in the state symbols for all of these. So they're all going to be aqueous. They're all inside a solution. Okay, so now to actually go on to the first step towards making it an ionic equation, what I'm going to do is split the different components, the ionic components, into their ions. So, for example, the potassium is going to be like K plus, bromine is going to be Br minus. But for Cl, right? For Cl, it's just going to be a molecule of Cl2. It's not really going to be slightly ionic or anything. So this is just going to remain the way it is, because we've got covalent bonds there, and the same thing with for Br2. So if I now draw this out, so Cl2 is going to remain the way it is, and this is going to have 2Ks, 2K plus, since I'm splitting it up, since we've got ions here, 2K plus aqueous, plus 2Br minus aqueous, and this produces the 2K plus aqueous plus 2Cl minus aqueous and Br2. Now, looking at this equation, what we can see is that we've got K plus on this side and K plus on that side. So in order to make this equation balanced, it is balanced already, but we could simplify it. So to simplify it, let's cancel out the K's on both sides. So K cancels out here, and it cancels out here. And then, yeah, we can't cancel out any of the rest of it. So we're just going to rewrite this equation underneath. So now this is the next step. This is where it becomes an ionic equation. So now we just have the reacting atoms in the final equation. So Cl2 plus 2Br minus react to form 2Cl minus aqueous plus Br2. And if you actually take a look at the oxidation numbers on this equation, on this ionic equation, we can see that oxidation number of chlorine here is going to be 0. The oxidation number of bromine here is going to be, let me choose a different color for this, is going to be -1. Oxidation number of chlorine here is going to be 1. No, -1. It's going to be -1. And the oxidation number of bromine here is going to be 0. So we can see as chlorine went from here to here, its oxidation number went down, so it's been reduced. and so therefore it oxidized something else, and what has been oxidized is bromine, because its oxidation number went up from -1 to 0. So yeah, as we can see, this is the displacement reaction, the ionic equation for the displacement reaction. So now we can use this same idea to fill out all of the different reactions which happen in this table, which are just three reactions. So chlorine and bromine, this is basically the reaction which I just did. So chlorine reaction with Br minus, and it's going to be Cl2 plus 2Br minus, react to form, and I'll just do it like react, the arrow pointing downwards produces 2Cl minus plus Br2, not, I don't need the 2, plus Br2, and all of these are going to be aqueous. Now, in this equation, what we need to do is basically swap the bromide ions for iodine. So Cl2 plus I minus, 2I minus, forms the 2Cl minus and I2. And for this reaction here, what's going to happen is bromine is going to react with iodine, and it's going to be Br2 reacts with 2I minus, and this forms 2Br minus and an I2, and this is going to be all of them are going to be aqueous, and in this one all of them are going to be aqueous. Now the color change, there's certain color changes which are going to occur when these reactions occur. We can basically take all of the colors of the ions here to be colorless, right? But for the atoms, the molecules, the diatomic molecules of these halogens, they have distinct colors. Well, for chlorine, not exactly. Chlorine is going to be colorless. So for this particular reaction here, what we're going to have, what we would observe if we just had the reaction like this, is we're going to observe a color change, and it's going to go from colorless, that looks like a G, colorless to, and it produces bromine, and bromine when it's in water is going to be aqueous. I mean, it's going to be a brown, an orangey sort of color, orange. So it goes from colorless to orange. Now when we take a look at this next reaction, chlorine and iodine reacting to produce 2Cl minus and I2, what we have happen is that the color change happens and causes to go from colorless, because Cl2 is colorless, goes from colorless to the color which iodine is in solution, which is brown. So it goes from colorless to brown. If we were to add like excess chlorine, what would happen is a precipitate would form, and that precipitate would be a grayish sort of color, like the color of iodine when it's solid. But anyway, moving on from that, if we have bromide, and this is the reason for that is because iodine, I2, is actually able to dissolve in Ki, so it can dissolve in the potassium iodide that's left, and so it would just be brown. Anyway, moving on from there, Br2, when it reacts with the I minus and produces I2, is basically going to be the same color, except that the beginning color is going to be different. So it's going to start off being the color of bromine in solution, which is orange, and it's going to go from orange to being the color of I2 when it's in solution, which is brown. So it's going to go from orange to brown. And so now let's actually think about this. Orange and brown are sort of similar colors. So it's kind of slightly difficult to tell the difference between them sometimes. So what we do to make it even clearer, right, is we often add, after this reaction has occurred, what we often do is add an organic solvent. And that organic solvent can be, usually we use something like hexane, and this is the molecule I have here, hexane. This is the space filling model. The space filling model. And if I was to draw out the displayed formula for this, so what it just looks like, it would be six carbon atoms. 1, 2, 3, 4, 5, 6. And they would be basically bonded like that. So we'd have hydrogens, and yeah, all of the hydrogens would basically be at the end of these lines, but I won't draw all of them. And this would probably smell something a tiny bit like petrol, and it would be colorless. At the start, this organic solvent would tend to be colorless. So when we add this, what happens is the ions, not the ions, the halogens which form actually dissolve in that solvent, and the color of the solvent will go from colorless to a specific color which is specific to that particular halogen. So now I'm going to move on to another table, and in this table we're going to look at the colors which they change to. So I've got here the different colors of the waters, so chlorine water, bromine water, iodine solution water, and I've got the potassium halogens, or the potassium halides. And so what's going to happen in these reactions here, right, is first of all the chlorine water will not react with the KCl. No reaction. And in fact, going back up to the other table which I had, there was no reaction here, 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 and here. So only the three in the top right basically had a reaction. So before I go on, I'm actually going to just write no reaction in those same corresponding boxes. No reaction. Whoa, my pen is like, yeah, let me pause this first. Okay, so I filled this out and we have like the no reaction boxes there. So now it's time to fill out the ones where there actually is a reaction. Before I go on to fill this out, let's just talk about the different colors which would form when the chlorine, bromine, and iodine molecules are in the organic solvent. So first of all, chlorine in the organic solvent. Chlorine in the organic solvent is going to be a pale yellowish greenish color. So pale yellow green. Bromine is going to be sort of its typical color when it's in the solution. It's going to be a orangey reddish sort of color. So it's going to be orange red. And iodine is going to be sort of its color when it is in a gas form. If you look for iodine gas, maybe on Google or something, you'd see that it's a sort of purplish violet sort of color, iodine. And this is the color that forms when it's actually dissolved in the organic solvent. The color it forms is a pinkish violet color, pink violet. These are the three colors which are formed when these specific halogens react in when they dissolve in an organic solvent. You might notice that I don't have fluorine here and I don't have astatine here, which are both elements which are part of the halogen series. And the reasons for this, fluorine is very reactive, and when these displacement reactions when you're trying to make these displacement reactions happen, fluorine is so reactive that it actually would react with the H2O so it would react basically with the water even before it gets a chance to react with these halogens. And astatine I haven't put in here because astatine is a very rare and very radioactive element, so it's not something you'd want to be handling in your chemistry laboratory. So yeah, anyway, so those are the colors which form. And now using these colors, and chlorine, I'm probably not going to be using this color here since it doesn't get displaced, since I don't have fluorine But using these colors, let's fill out this table. So what's gonna happen when we react the chlorine and the bromine and the chlorine and the potassium, the chlorine water and the potassium bromide, and add the organic solvent? So the color we're going to observe is going to be the color of when bromine Br2 is dissolved in organic solvent, since that's what's going to be produced when KBr gets, then when the Br in KBr gets displaced. So it's going to be orange red. So I'm just going to write into this box orange red color on addition of organic solvent. And the reason why I write on addition of organic solvent is because before the organic solvent is added, it's going to be its orange color. So now let's go on to Ki. When it reacts with Ki, I2 is going to be produced. And as I said, iodine is a pinkish violet color. So there's gonna be pink / violet color. And I didn't put a U in here. It's kind of the American spelling. Let me put a U in here. On addition of organic solvent. And moving on to the bromine and potassium iodide reaction, iodine gas is going to be produced again. So it's basically going to be the same. So pink / violet color on addition of organic solvent. So these are the colors which are going to be produced on these reactions. And yeah, so I hope you guys found this video helpful, and I'll see you in the next video where I'll be talking about the different things you can the way you can use this information in a situation where you have an unknown halide solution. So yeah, see you guys in the next video.